Hello everyone, and welcome to the video that I've made for section 9.2, working with parabolas. This will be the first section where we're really getting more in depth with the different conics. In 9.1 we just kind of gave a quick idea definition of it, but this one will really delve into parabolas and the work we need to do with those. So the skill objectives for this particular video. Number one, we're going to graph a parabola given a focus, vertex, and directrix. Number two, find the equation of a parabola given its vertex. And number three, solve applied problems using parabolas. The conceptual objectives for this video are number one, derive the general equation of a parabola, and number two, identify, draw, and use the focus, directrix, and axis of symmetry to go through and actually give a graph. So that's where we're going to be going. Let's take a look at the next slide. Just a quick bit to review. This is a definition that we saw last time in 9.1, but we have the definition of a parabola is the set of points in a plane that are equidistant from a fixed line called the directrix and a fixed point not on that line called the focus. So when we're looking at this, we see in blue here, this is the axis of symmetry. The focus is right here, the directrix is here. Every point that's on the parabola is going to be the same distance from this focus as it is the directrix. Now, some other important pieces of information that you have here. First up, the vertex. The vertex is the point that is directly halfway between the focus and the directrix. And then we do have this axis of symmetry. The axis of symmetry a lot of times is how we're going to go and classify a parabola. We'll ask, does it have a vertical axis of symmetry or a horizontal axis of symmetry? The axis of symmetry will always be perpendicular to the directrix. The other thing I want you to realize here is that this vertex is halfway between there, and there is the distance between the vertex and the directrix, or the vertex and the focus, is always defined as p units. So again, as I mentioned, when we go through, when we look at a parabola, we are going to be looking at its orientation. And initially, for where we're at right now, parabolas are either going to have either a vertical or horizontal axis of symmetry. So when we have a vertical axis of symmetry, I'm going to have a parabola like this one here that opens up, or I could have one that opens down. We have the focus, the directrix, and the vertex, and that distance p units. When you have the horizontal axis, so here in white is the axis of symmetry, we have a parabola in this case that is going to either open left or right. Now this one happens to open right, and that's also going to be part of your analysis. In this case, so there's the directrix, axis of symmetry, the focus, and the vertex is right here, and that distance p units that we have between the directrix and the vertex and the focus is right there. Okay, now let's take a look at the equations of these different parabolas. Now, for our purposes that we're working with, if you remember the equations for the conics in 9.1, there was always that b term. Right now, that b term is resulting in a rotation of axes. We are not going to be worrying about the rotation of axes right now. So the b value is not going to exist. You won't have an xy term. But the other thing you'll remember on that is that they were in the form of ax squared plus the cy squared plus dx plus ey plus f equals 0. Those are not in forms like you see here with the horizontal axis symmetry and the vertical axis symmetry. One of the things you're going to have to do, and we'll see an example coming up, is that when you go through to go and put these things into the standard form, you're going to be using completing the square. Right now, it's not so bad. You're just going to have to complete the square on one variable. The other conics moving forward, you might have to complete the square on 2. But let's just take a look at the parabola right now. In this case, when we have a horizontal axis of symmetry, the standard form for this equation is the quantity y minus k squared equals 4p times x minus h. Now that p value does represent the distance between the focus and the vertex and the vertex and the directrix. So from this information, what you're able to locate is you're able to tell me where the vertex is at. The values of h and k form the coordinates of the point of the vertex. Remember, it's like whenever we've seen that x, y minus k and the x minus h in the past, the h and k here are going to have the opposite sign of what you see in the problem. The next one is the focus. P can be a positive or negative number. Okay. In fact, if P is greater than 0, this opens right. If P is less than 0, this is going to be a parabola that opens left. But regardless of what that P value is, whatever P is, be it positive or negative, to locate the focus, I'm just going to plug that number in here, and the focus will be at P plus H, comma, K. The directrix is going the other direction from the vertex. If the focus moved to the right, the directrix is to the left of the vertex. And if the focus is to the left, then the directrix is going to be to the right of vertex. So in this case, whatever happens, again, taking whatever value you have for P, the directrix will be a vertical line at x equals the opposite of whatever P is plus H. The axis of symmetry is y equals k. And again, when P is positive, it opens right. When P is negative, it opens to the left. Now, if you have a vertical axis of symmetry, then you'll notice that the x minus h and y minus k have switched places. So you now have the standard form for a parabola that has a vertical axis of symmetry is going to be the quantity x minus h squared equals 4p times y minus k. Again, the vertex is still at HK. That doesn't change. The vertex, you're going to see HK show up in the other conics as well. Not necessarily vertex, but for parabolas, the vertex is always HK. But the other thing that happens here is when you have a vertical axis, the focus is either going to be above the vertex or below the vertex, and same with the directrix. If the focus is above the vertex, the directrix is going to be below the vertex. And if the focus is below the vertex, then the directrix would be above the vertex. So in this case, again, you take whatever P is, the focus is going to be at whatever H is, comma, the value of P plus K. And the directrix is going to be the horizontal line, y equals minus P, the opposite of P, plus K. The axis of symmetry is going to stay at x equals h. And again, when P is positive, it's opening up. When P is negative, this parabola is going to open down. So when you're going to need to put the equation, sometimes they'll give the equation in the standard form already. If not, you're going to have to complete the square to get it in that standard form. And then you can pull this information, all that information, out from that equation. Let's take a look at an example. Let's take a look here graphing a parabola. So in this case, what we're going to do is we're going to sketch the parabola. I'm going to go through, identify the vertex, the focus, and the directrix, and then we'll graph the parabola. And all we're going to start out being given here is this equation. The equation of the parabola is x squared plus 2x plus 8y minus 7 equals 0. Well, in this case, right away, I know that this one is going to have a vertical axis of symmetry. And I know that because I have an x squared here. And because of that, I know I'm going to complete the square on x's here. So I'm going to end up with a quantity involving x squared, which is the form of the vertical axis of symmetry. So I start out by this one. I'll go through, and you remember completing the square, we wanted to isolate these. Well, we have an equal sign. So to isolate it, I just subtracted 8y and added 7. So I now have x squared plus 2x equals negative 8y plus 7. At this point, remember completing the square. What you do, you take half of that value, in this case the coefficient on x. I'm going to take half of that number and square it. So in this case, half of 2 is 1. So I'm going to add 1 squared to the left. Because I added 1 squared, and 1 squared is 1, I need to add 1 to the right as well. So that's why this plus 1 there. If this had been something like a 4, then I would have added a 2 squared, then I would have added 4 over here. But because I had a 1 squared, I'm just adding 1. Now the reason we complete the square is because of how this is going to factor. X squared plus 2x plus 1 will factor as x plus 1 times x plus 1, or x plus 1, that quantity squared, and that equals, when I combine the like terms here, negative 8y plus 8. And then when I go through just to put it in that proper form, I'm going to pull out a factor, because remember in that standard form, the standard form on that is it's going to be 4p times y minus k. So I've got to go through, pull out whatever the coefficient on y is, I have to pull it out. If that means I'd have a fraction, so be it. I'll have to do that. But in this case, I'm okay. I just pull out the negative 8, and I have y plus 1, that quantity squared, equals negative 8 times the quantity y minus 1. So again, we have a vertical axis of symmetry. We know the vertex is at negative 1, 1, because it all h is negative 1, k will be a positive 1. Negative 8 happens to equal 4p. So in this particular problem, I know 4p equals negative 8, so p will equal negative 2. That's how we got that value. So I know that in this case, since it's a vertical axis, I'm going to go and add p to the negative 1 to get to the focus. So in this case, I will be at negative 1, because 1 plus a negative 2 is going to be negative 1. And then to get the directrix, it's going to be y equals the opposite of p, which will be positive 2 plus 1, which gives me 3. So now what I'm going to need to do is I want to sketch this thing. Well, the first thing I want to do on here is locate the different points that we have. So to start out with, I know the focus is at negative 1, negative 1. So it's going to be, my focus is going to be right here. I know in this case that the vertex is at negative 1, 1. So it's right here. And I also know on this problem that the directrix is y equals 3. So it's going to be this line right here. So there's what we have. And now I want to be able to sketch this thing. Now, we do want to go through and have a little bit of accuracy on this. And one of the things that we have, another thing we have that I haven't mentioned yet, is what's called a focal segment. It is a segment that goes through the focus. And there is a special focal segment that's parallel to the directrix. And that focal segment is called the lattice rectum. And the length of that lattice rectum is always equal to, the length is 4 times the absolute value of p. So basically, the absolute value of whatever you have in front of, like in this case, the y minus 1. So I know in this case, the length of my lattice rectum is going to be 8. And so if I go 4 units from the focus, I move 4 units to the right, I'm here. If I move 4 units to the left, I'm here. Those are going to be 2 points that are also on this parabola. And so if I want to sketch that one, the vertex is here. I know I'm just going to come through here, go like that, and do it from the other direction as well. And there's a representation of this particular parabola. Now let's take a look at finding an equation. In this particular problem, what I have is I'm going to find the equation of a parabola with a focus at -2, 3 and a directrix at x equals 4. Now, on this problem, what I tend to do on something like this, just to get a feel for it so I can see what I'm working with, right away I know I have a vertical directrix. So I know for this particular problem that I have a horizontal axis of symmetry, and the axis of symmetry is what you see in yellow there. So I know the standard form for this parabola is going to be the equation y minus k, that quantity squared, equals 4p times x minus h. So what I have to do on this one, and this is one that's going to be probably the trickiest that I could have, in that you don't have the vertex. We know the vertex is hk, so the first thing we have to do is we have to figure out how we're going to find that vertex. We know the vertex is always halfway between the focus and the directrix. So this vertex is going to be halfway, it's going to lie on this yellow line, and it's going to be halfway between this point right there and that line. Well, if you look at this one, you'll notice that this distance right here, that goes from x equals -2 to x equals 4, so that is 6 units. The other thing you know is that while the distance from the focus to the vertex is p units, and the distance from the vertex to the directrix is p units, that means that the distance from the focus to the directrix will be 2p units. So therefore I know 2p units is equal to 6, so p is equal to 3. And because of that, I know that if I move 3 units from the focus, and I place that, that is going to be where I'm going to have my vertex. So in this case, I'm at -2. When I move 3 units, I'll be at the point right there. The vertex here is going to be at the point 1, 3. Now, the other thing I need to do on this one is I need to go through, I have to realize what's happening on this parabola. Because remember, this value of p that I have right there also indicates the direction if this thing is opening for this particular parabola, if it's opening left or right. Based on the diagram, I know this particular parabola is got to go and open to the left. It's going to come like that, what you see with the pointer. So in this particular problem, I know p, the p up here, this p value has to be less than 0. So therefore that p will be equal to -3. I also know, because the vertex is at the point 1, 3, I know h is equal to 1 and k is equal to 3. So the equation for this particular parabola in standard form is going to be y minus 3, that quantity squared, equals -12 times x minus 1. There's that equation for that particular parabola that's described right there. Now, before we go on to the application problems, one of the things I think it's important for you to understand is the reflective properties that exist with a parabola. And these reflective properties have a lot of bearing on things that you use and you like to do. For example, this point right there, that's the focus. That's not called the focus just randomly. There is a reason for that. One of the properties you have with a parabola is that one of the things is that when things, if that parabola represents a reflective surface, then there will be things that can come into that parabola. It'll hit that surface, and the reflective property is that the reflection will send it right to the focus. So something coming in here like this will hit the surface, bounce to the focus. Something coming in here will come down, hit the surface, bounce to the focus. Or here, hit the surface, bounce to the focus. So really what happens here is that focus serves as a gathering point for a lot of different things coming into that parabola. Another property that you have is that things that come from the focus, you send something out from the focus, it will hit that reflective surface and it will cause it to bounce straight out. It doesn't matter where it's at, it will bounce straight out like this, there, and in essence, creating a beam. Now, where do these things come into play? Well, this first one, what you see in this situation where the signals were coming into the parabola surface, bouncing off and going to the focus. One of the places where this is really probably is the most important to all of us is something that you can see on people's houses or outside communication companies. And that thing is called a satellite dish. If you think about a satellite dish, there is an arm that sticks up. That arm is where the receiver is, and that arm is located right at the focus. So signals are coming in. The signals coming in are very weak, but the signals come in, it bounces to that receiver, it collects the signal, and it's able to then generate a image or sound that we watch on TV or listen on radio or whatever. The other one you have here in this situation is where we have where it's coming from the focus. Something is being emitted from the focus and going out when it hits a reflective surface. Those of you who are doing anything in the theater, you know this is very important because what you're looking at right there, this is where the bulb is. And it will come out, hit the surface, and you go through, and this is stage lighting. But it's not just stage lighting. Another thing, if you happen to go take a look in your car, look at the headlight of your car. If you look in there, you'll notice that it is a smooth, reflective, curved surface. It is a parabola. The bulb is located at the focus, and it comes out and sends the light out in a beam so that you're able to drive. So these things really come into play in terms of for their reflective properties, really affect what we have and what we do each day. Now let's take a look at an application problem. And here we are with a satellite dish. So in this problem, what we have is we have a satellite dish that is 24 feet across and 4 feet deep at its center. And we want to know where should I place that receiver? How far, how high above our surface, our vertex, if you will, that center point, how high above that should that receiver be placed? Well, here's what we do. One of the things is that, in this case, we'll want to go through and draw a parabola that can represent the edge of that satellite dish. Okay, and one of the things that we can do, because we don't have a vertex, I'm going to make my life easy. I'm going to put the vertex. I'm going to let that vertex be at 0, 0. I'm going to make my life easy with that. And because of that, I can go through and do what I did with this drawing here. The vertex is here at the origin. And because it's 24 feet across, I went 12. I just put a mark at 12 and negative 12. And I put a mark up here at 4. And so I have these 2 points up here. This point is at negative 12, 4. And that point here is at 12, 4. And those are points that are on the parabola. Okay? So what I do on this one, I know that this thing is opening. It opens up. And because it opens up, I know that H and K are both 0. So that standard form for this particular parabola is going to be x squared equals 4p times y, because it'd be x minus h, which is x minus 0 squared, and times 4p times y minus 0 squared. So I got x squared equals 4p times y. And so what I'm going to do here is I'm going to plug in one of my points in for x and y and solve for p. And I know that P is the distance that I need to go and place the receiver, because the receiver is going to be at that focus. So if I can find P, then I'm all set. So in this case, I put 12 squared equals 4 times P times 4, or I get 144 equals 16 P. Divide by 16, and I get that P then is equal to 9. So therefore, for this particular problem, I need the receiver to be 9 feet above the center. So with that, this video is completed. You just need to remember on the application problems to make sure to use the fact that a lot of times they're not giving you a vertex to go and make it as easy as possible. Put that vertex right on the origin. So with that, we will end this video, and I will see you in class.